Hello everyone, my name is Yang from Elehear. Today we present our work end-to-end multi-channel targeted speech enhancement system based on a live SpeechNet for the third Clarity Enhancement Challenge. This work is a collaboration with Jiang, Guo Zhihao, and Eric Miao at Elehear. My presentation will cover the following parts. The first one is system overview. Then we will talk about the model details. After that, we'll discuss our loss function and training strategy. Finally, we'll talk about the results and the conclusion. The system overview is next. First, the 6-channel noisy speech signal is transformed into the frequency domain using STFT. The frequency domain signal is then encoded using encoder. Simultaneously, the enrollment wave is processed through a SpeechNet to obtain a speaker embedding. The encoded signal and the speaker embedding are fused through speaker adaptation. The fused signal is fed into the target speech enhancement module, and the processed signal is decoded to get the denoised frequency domain signal. Finally, the denoised signal is transformed back to the time domain using inverse of STFT to get the final estimated speech. Now let me introduce the module details. The STFT uses a 512 windlass, 80 hopless, and a hanging window. The encoder uses a chiral convolution word dimension with kernel size 1 at 5. The input 6-channel STFT real and imaginary parts are concatenated to get 12-channel inputs. About the SpeechNet, we speaker box celebrity ResNet 34 from Hugging Face to get 256 dimension speaker embedding. The speaker adaptation we use feature-wise linear modulation. About the decoder, we use a simple linear layer. The targeted speech enhancement module repeats 8 times, each composed of an intro block and 2 inter blocks. The intro block is designed to model frequency domain information, while the inter block focuses on modeling time domain correlations, as shown in the figure. The intro block is a sequential cascade of a frequency convolution module, a full-band linear module, and another frequency convolution module. A frequency convolution module includes a layer norm, a frequency group convolution, one dimension, and a period activation. The full-band linear module consists of a layer norm, a linear layer followed by a silo activation, a group linear layer, and another linear layer followed by a silo activation. The interblock includes a layer norm, a member block, and a dropout. In the experiments, we use a dropout rate of 0.1. Now let's talk about the Mamba S6 structure. The Mamba module integrates a structured state space model with convolution and linear projection operations to process loss sequences effectively. Let's break this down step by step. The left diagram is a Mamba block. It starts with a linear projection to expand upon the input embeddings. Then a convolution before the selective state space model is applied to help capture short-term features. The state space model is responsible for modeling temporal dependencies within the input sequence. It can model long-term information with reduced computational complexity. The right side is a gated structure module. Finally, the output dimension is reduced through linear projection. The right diagram is a structured state space module. Its structure lacks a recurrent neural network module, but it didn't have activation. Now we talk about loss. To ensure optimal training, we use two primary loss functions, SR-SNR and MRL loss. The SR-SNR loss formula like this. And the multi-resolution loss employs different STFT configurations with various FFT size, hop length, and wind length to capture phi grade and cos grade features. Then we use the sum of magnitude loss, asymmetric loss, and real and imaginary loss. Here we use asymmetric loss to avoid oversuppression. Let me talk about the training configuration and strategy we used. About the training data, we use Clarity Enhancement Challenge second and Clarity Enhancement Challenge third task 2 and task 3 training data, all separate at 16 kHz. And the 16 kHz reference lift channel was used as a target for the training process. About optimization details, we used Adam weight optimizer, and the learning rate was set to 0.001. And we implemented a learning rate schedule based on the reduced LR or plateau strategy, adjusting every 3 epochs with a patience factor of 0.5. Additionally, we applied a gradient clip with a threshold of 1 to stabilize the training process. Our training strategy consisted of 3 stages. First stage, we treated the model using the Clarity Enhancement Challenge second dataset until the model convergence. Second stage, we use the model from the first stage as the initial model, and we fine-tuned it with the Clarity Enhancement Challenge third task 2 dataset. At the third stage is similarly to second stage. We took the model from the first stage and further fine-tuned it on the Clarity Enhancement Challenge third task 3 dataset. Finally, we use NER-NL2 for hearing loss compensation. First, we calculate NER-NL2 compensation parameters for each sample based on the audiogram. For wide dynamic range compression, we need to get the compression threshold and compression ratio for each frequency band, like right picture. Set the limiting threshold at -5 dBFS with a limiting compression ratio of 0.001. For equalization, we need to calculate the gain for each frequency band. Next, we will process each frame of the signal. First, we will perform frequency domain processing, including WDRC and echo. Then, perform time domain processing using a compressor. This is about our results. The complexity of the model is 57 G-flops, and the model size is a ResNet 34 SpeakNet model with 60.6 million parameters, and a TSE model with 60.7 million parameters. About objection evaluation, the high-speed score of task 2 is 0.75. The high-speed score of task 3 is about 0.61. Then from 10 listeners' listening tests, the task 2 score is 88%, and the task 3 score is 77%. This is an example of our results from task 2 development. The first one is noisy speech. The second one is the target speech.
I'm fed up with your reading anyway.
The third one is our estimated signal.
I'm fed up with your reading anyway.
The last is our estimated signal processed by Miao NL2.
I'm fed up with your reading anyway.
There are still some issues. First is the design of window function in the STFT. Our window is symmetric, which places too much emphasis on past information. Design an asymmetric window that gives more weight to the current input may yield better results. Second, inspired by TF GridNet, the second member network can be modified into a grid structure to simultaneously load time and frequency domain information. This may get better results. This is all about my presentation. Thank you.